the traversability, or not good representation for estimating the traversability of the terrain. First of all, it makes impression that most of the vegetation is not traversable. Second of all, it suffers from reflectivity of the terrain. So, for example, if the surface is wet, then the slum reconstructed terrain contains huge holes, and it is hard to estimate whether it is traversable or not. So, instead of using this slum reconstructed terrain for estimating the traversability directly, we have decided to predict something which we call supporting terrain. So supporting terrain is some kind of hidden layer of terrain which is not directly observable either by camera or lidar, but it is something that will support the robot body during its traversal. So, for example, for this case, it could look like that. And we would like to learn a convolutional network which takes lidar scans and camera images and predict this supporting terrain. And it is not easy to directly manually estimate some annotations for this supporting terrain. So instead, we have decided for self-supervised way where we learn this supporting terrain from recorded robot trajectories. So basically, the idea is similar to what we have done with Patrick and Aved. So we will use the future measurements, in this case, the poses of the robot on the terrain, as a privileged information which allows to learn the parameters of this convolutional network. And in order to do it, we construct something which we call post-consistency loss, which actually express the physical consistency of the measured robot trajectory and the predicted height map. And then when we have it, we can just simply backpropagate through this loss and learn the parameters of the network. And in order to construct this post-consistency loss, we start by introducing very simple physical model. So we've got almost no experience with physics, so the model is extremely simple, but it can be like easily enriched by some more complicated stuff if someone who knows the physics of the vehicle or terrain, tire interaction, and so on, how it works. So the model we have used works as follows. So we've got height map, and we've got model of the robot, which consists from weighted point clouds, just a set of 3D points, each associated with the weight. And we've got flipper position, it's like 4-dimensional vector, which encodes the position of this red auxiliary independently articulated subtracts, flippers. And given this height map and the model of the robot, the question is, what will be pose of this robot on the terrain? And our simple model says that the corresponding pose of the robot will be the pose which minimize the potential energy of the robot on the terrain while respect the collision-free constraints. So basically it says that the body of the robot is not in collision with the terrain. So if you look at it, so we are optimizing over the pose of the robot, which consists from roll and pitch, denoted by alpha, and vertical position of the robot denoted by T. And you just minimize potential energy, which is in this case just weighted sum of point of vertical position of the points on the robot, subject to constraints which basically say that all of the points on the robot model have to be above the height map. And so the result of this optimization could end up this. So we will obtain some like minimum potential energy poles on this terrain, and this is the feed-forward path. And now the question is how to backpropagate, because we recorded poses and we would like to know what height map corresponds to recorded poses. And
so, sorry, I have a very stupid question. So why the robot is how the robot is forced to stick on the ground? Why it's not flying somewhere?
Because it's minimized potential energy. So it basically minimized the height of all the points on the robot model.
Okay.
So it's just pushing, this minimization procedure is pushing the robot model as low as possible, but it says that all of the robot model, all of the robot points have to be above the height.
I forgot the equation for potential energy. Okay, thank you.
So that's essentially this thing right here.
Yeah.
So it's just
G is gravity.
Yeah. So because it's important to understand that the points, the small, so it's rotating, but essentially the points are, the robot itself. So that's are these balls which the robot is created of. So it's really a set of points, and they should be as low as possible.
Yeah. Thank you.
So if you look at the output of this optimization, it's more or less like obvious what's going on inside, even without like proper understanding what could be every single symbol. Okay, so now just to learn from recorded poses from this red alpha and t, we need to backpropagate through this optimization problem. And before we do it, let me just mention one more thing. So given one pole, there are multiple height maps which are physically consistent with this pose. So for example, you can visualize this in such simple 2D sketch where vertical axis corresponds to the height map axis and the horizontal axis corresponds to pose axis. And given one pose of the robot, there are multiple different height maps which are physically consistent with this pose. And given another pose, there are different height maps which are consistent with this pose. Due to this low dimensional visualization, it makes impression that most of the height maps are consistent with given pose, but the space is actually quite sparse. So in the high dimensional space, it's quite rare even that something is physically consistent with a given pose. And these tuples of physically consistent poses and height maps forms some, I would say, like physically consistent set. And there are, of course, tuples which are physically inconsistent. So, for example, height map which is collision with the robot body, which is shown in left upper corner, or height map that insufficiently supports robot in its pose. So it's shown in right bottom corner. There are also some funny examples of real-world inconsistencies. The upper left one comes from the LG advertisement for LG displays. They are that realistic that it makes people scared. The other one comes just from some simple pranks. Okay, so let's go back to the original problem. So what we do is that we are not enforcing any specific height map, but what we say is that arbitrary height map that satisfies necessary conditions for making the recorded pose to be the optimum of this constraint optimization problem is physically consistent with this height map. So I will just now write it more formally. So what I say is that any height map that satisfies necessary conditions, where necessary conditions for the optimality of constraint optimization problem are typically considered as this Kuhn, Karush, Tucker conditions. So we will construct them explicitly. So what I will do is that I will construct first Lagrangian, which consists from criterion and lambda times constraints. Each lambda is called KKT multiplier, and each point on the robot model is connected with its own KKT multiplier. And if I take this Lagrangian and build this KKT conditions, so they consist from stationarity, complementary slackness, and primal and dual feasibility. So simple physical interpretation of these conditions is as follows. So as I have mentioned,
just Carla, sorry, could you please remind me the constraint less than equal to 0? Then, as I recall, the Lagrangian is essentially for the equality to 0, isn't it? Is it okay in that way?
So basically, if there are inequalities and equalities, then Lagrangian is constructed from both of these things. There are some multipliers for equalities, some multipliers for inequalities. And for equalities, just the stationarity is enough. And for inequalities, all of these four conditions has to be satisfied.
Okay, got it. Okay.
And also some regularity conditions have to be satisfied. So usually in this slide, mathematicians got a little bit aggressive and start to say that this problem is not convex. So the typical regularity conditions where this KKT conditions works properly is that the problem is convex. Then this condition is called like Slater condition, and then you can use this KKT condition. It is not satisfied here because the robot can be, so if you imagine some swing, then the robot can be located in multiple different positions, which minimize its potential energy on such swing. It could be like located on the left or on the right, or it could be in unstable equilibrium if it is supported only on 2 points on its body. So it's not convex. Fortunately, it satisfies other regularity condition, which is called Mangasarian-Fromovitz. And I will not go into the detail, but this condition basically says that if any constraints are active constraints, then there have to exist a direction which makes them inactive. So in this case, it's simple. The active constraints are those which correspond to the points which are in contact with the terrain. And the direction is simply the vertical direction, like 0, 0, 1, in which you can just lift the robot body and make these constraints inactive. So just to make sure that everything works, so also the regularity condition is satisfied. Anyway, so we've got this condition. Physical interpretation of this condition is that I have mentioned that every point on the robot model is connected with one KKT multiplier, lambda. And so if you look at the complementary slackness, it basically say that non-zero lambda is allowed only for points which are in contact with the terrain. So in the other words, in points where the robot is supported by the terrain. And if the robot is not supported, then the lambda is forced to be 0 because this subtraction is bigger than 0, and you enforce this like to be equal to 0. And then the stationarity condition just makes sure that the support of the robot body is sufficiently distributed along the robot body in order to fix all of its degrees of freedom. So in this case, it just fixes the rotation and translation in the vertical axis. Okay, so it doesn't matter. So basically what we have is the constraint optimization problem. We can build this condition, and whenever these conditions are satisfied, we say that the height map is physically consistent with the recorded pose. And in order to backpropagate through these conditions, we basically measure the Euclidean distance from these conditions. And so we build the loss we construct the loss as a Euclidean distance from this condition. So I will do it like that, like explicitly. It will be nothing more than the Euclidean distance. And that's it, more or less. The only issue which remains is that this loss contains some inner minimization over these lambda multiplier, over these KKT multipliers. So these KKT multipliers are basically some auxiliary variable we need to get rid of before we will backpropagate. Fortunately, if you look at it, the criterion of this inner minimization depends on lambda only quadratically. So, and the only condition on the lambda is that lambda have to be above 0. So this inner minimization loop can be efficiently tackled by non-negative least square method. And now you can work with it. So, for example, whenever this KKT is 0, or KKT, this loss is 0 for physically consistent set, and it's growing proportionally to the distance from this physically consistent set. The physical meaning of its values remains unclear for me, but maybe someone will be able to help me to understand what's going on exactly. But it's just
okay, I understand
from this
that's actually I just wanted to ask about the meaning of the losses. And is it somehow smooth in a way that something that would correspond to the physical understanding, the problem, like if the robot is floating just above the terrain, the error is small. So I don't know. I mean,
so the higher this floating, the larger the KKT loss. In this case, it probably works.
And it's a sum over 3 or over all the points, right?
So for now, I just spoke about single poles. So for single poles, you can simply, so if someone gives you single poles, which is now outlined in this 2D sketch by this black cross, and it gives you poles and it gives you some height map, then you can easily backpropagate and you can try to decrease the value of this loss in order to obtain some better height maps or physically more consistent height maps. And for the whole trajectory, you can simply generalize the whole approach by saying that the KKT loss of the whole trajectory is just the same, is the summation of KKT losses over all recorded poses in this trajectory. So here I visualize it by four black crosses, which corresponds to 4 robot poses in a single trajectory, and you can gradiently optimize the summation, and you can obtain something like that. And then the reconstructed height map for the whole trajectory could look like that. And now let's go back to the original problem. So I promise that we will connect this KKT loss to the convolution network in order to learn to predict this supporting terrain. So you can do it. You can simply connect the KKT conditions or distance from KKT conditions as a loss from which measures whether the recorded ground truth trajectory of the robot, poses of the robot, sequence of poses of the robot is physically consistent with the predicted height map, and you can directly learn parameters of the network in order to predict physically consistent height maps. So experiments are as follows. So it's like pretty straightforward, nothing super impressive happens. So if you look at the bird's eye view of slum reconstructed terrain, robot is located in the left bottom corner and the color encodes the height of the terrain, then it looks like that. And if you compare it with predicted supporting terrain, you can see that, for example, height of the grass or vegetation is significantly suppressed, while the height of the rigid objects such as walls, stones, trees, cars, and so on is preserved.
Maybe one question.
Yeah.
So when the robots in the trajectory have driven over the vegetation, then it is from the visual features, it will learn that since this is traversable, then if I see it again, I will assign a lower height.
Yeah, something like that.
Like this, yeah.
Maybe, yeah, exactly like that. Okay, and yeah, there are some numbers which were necessary for publishing the stuff. So, for example, if you compare this approach with other approaches, then you can get better terrain reconstruction, and also you can achieve, if you use this predicted supporting terrain to estimate the roll and pitch of the robot, then you can have better estimation or lower error when estimating or predicting the roll and pitch of the robot on this terrain, which is crucial for estimating the traversability of the terrain.
And this model was trained only from real data, or was it trained also on some virtual?
I guess
simulation?
no.
Just
I think that it was only from real data.
Okay, so you drove a lot of
yes.
A lot of kilometers with the robot over different terrains, actually. Then you measured the proper, so as you said, the vertical acceleration, and then also.
So here we basically did not measure the vertical acceleration. We just measured the poses of the robot. So here we use, for example, inertial measurement unit, magnetometer. Also we use SLAM in order to estimate as precise as possible poses of the robot, and then we say, okay, so whatever you will predict, it has to be physically consistent with this recorded poses of the robot.
Okay.
And well, I'm just suppressing one trick which has been also used. We have also taken one special data set on a rigid terrain, and then we reconstructed this rigid terrain, and we also learned to predict this rigid terrain in fully supervised manner. But yeah, it just helped to regularize the whole learning process. Of course, that you have to use also this flexible terrains in order to learn to suppress it somehow. So I'm just trying to be as open as possible. Okay, so and recently I've also done some very preliminary experiments where I try to optimize both height map and the position of the robot simultaneously. It is not fully related what we could do for Valeo, but maybe it might be interesting as well. So what we have said is that the only things which can be accurately measured is typically roll, pitch, and yaw of the robot using the inertial measurement unit and the magnetometer. It has surprisingly low error. And you can also measure track velocities and flipper position using the motor encoders, which is also kind of reliable thing which can be easily measured on board. And given this, we have decided to optimize the poses of the robot, the positions of the robot along the trajectory, and the height map simultaneously. And if you do it, it looks like that. So here, both is moving, the height map and the poses of the robot. And on right bottom corner, you can see how the optimization works. Here we did not connect it any convolutional network, so the optimization can be actually tackled more efficiently. It could be either like a sequence of quadratic programs or linear programs, depending on what kind of norms you are minimizing. So here I use like L1 norm instead of L2 norm because it was faster to optimize, and it works kind of reasonably, one would believe. So here the only input is the velocity of tracks and the poses, roll, pitch, and yaw of the robot, and the output are XYZ poses and the height map, which is under the trajectory of the robot, which makes the whole trajectory physically consistent.
So you said that there are some fixed parameters like the position of the robot, yet you optimize.
So XYZ of the robot body is optimized, and roll, pitch, and yaw is fixed. Because surprisingly, inertial measurement unit can accurately measure this roll, pitch, and yaw, but the XYZ is kind of issue. And especially when SLAM fails or the lidar does not work or camera does not work, then it's almost impossible to estimate XYZ reliably. And just for fun, we have also tried some kind of like blind, I call it blind SLAM with blind loop closure. So basically it's like standard SLAM, but without any exteroceptive measurement. So here we completely ignore camera, we completely ignore lidar, and we just say, okay, we have measured the inclinations of the robot, roll, pitch, and yaw, and we know the position of the flippers and the speed of tracks, and that's it, and optimize the trajectory and the height map simultaneously.
So for exactly the same input as on the last slide, right?
Yes, exactly. But here is loop closure, so it makes more impression that it's like closer to the SLAM.